when we drop something, it accelerates downward due to gravity. Of course, dropping this might be troublesome. So, what is the magnitude of this acceleration? You might notice that after you let go of a very light object, it accelerates much less and then just stops accelerating compared to a denser object that has less air resistance. Regardless of the final velocity, the acceleration due to gravity is around 9.8 meters per second squared near Earth's surface. Many questions, such as say on the MCAT or on other multiple choice exams where you are supposed to approximate, will ask you to use 10 meters per second squared. We usually think of up as positive, and since gravity, its direction defines down, well, gravity is usually treated as negative. Free fall is the acceleration due to gravity of an object in the absence of air resistance. If we let go of a feather compared to letting go of a bowling ball, well, the feather obviously falls much slower. In fact, for a very long time, people thought that lighter objects fell slower than heavier objects, according to Aristotle's thought. There's a problem with Aristotelian thought in the terms of, hey, what happens if you chain a light ball and a heavy ball together? Well, if you chain them together, or even just glued them together, or tied them together with a rope, which is one continuous object, where it's chains, you can argue that they're separate, then in total, the two objects are heavier than the heavy ball, which means they should fall faster. But, according to Aristotle, the lighter ball should fall slower than the heavy ball, and therefore tug the heavy ball up and slow it down. So this paradox is something Aristotle apparently never considered. Either that, or... well, Aristotle did a lot of thinking. The old Greek philosophers did a lot of thought experiments. The problem with thought experiments is that they aren't actual physical experiments, which can reveal many other things. That feather and that bowling ball example, if you drop them in a vacuum with no air resistance, they fall at the same speeds at the same times. They accelerate the same. And free fall has two assumptions. First, the free fall acceleration has to be constant or uniform over the range of motion, and it is directed downward. This is generally true over short distances because if you get farther and farther away from, say, Earth, the gravitational field intensity decreases. The effect of air resistance is negligible in free fall scenarios, which, well, it works fine in a vacuum tube, but generally near Earth's surface, no. Everybody knows that if I drop a wad of paper, a wad of paper versus if I drop a calculator, they're going to have different amounts of air resistance relative to their mass. Of course, if I scrunch the paper up tighter, it has less air resistance compared to if I didn't scrunch it up so tight. Now, uniform vertical acceleration has a characteristic that in reality it doesn't work, because objects eventually, as they get faster and faster, more and more air is smashing into the bottom side of the object, and, well, that gives a force on it. The force of air resistance will eventually equal the force of gravity, and the object stops accelerating and stays at a constant velocity. This is called terminal velocity. People jumping out of airplanes can make nice, neat formations in the sky at the same level, all holding hands, despite the fact that they jump out at different times, because, well, if they tuck their arms in, and legs in as well, they present less surface area and thus have lower air resistance and can accelerate to a higher terminal velocity. And thus, they can catch up to the first people who are all nice and spread out. And all those first people who are spread out have a lower terminal velocity, so they can be caught up. Of course, once the parachute's open, they have much lower terminal velocities. The purpose of a parachute is to make your terminal velocity small enough that you can survive the landing. Although a lot of people still do get ankle injuries from bad landings. Okay. Another issue with uniform vertical acceleration is, well, sometimes you realize that down is a direction that changes all the time. Like in orbit. Weightlessness is caused by the force of gravity holding something where it is compared to the things around it. This space station, the International Space Station, is falling forever toward Earth. It's always falling, but because the Earth curves away from it, it can never catch up. Well, until we stop giving it altitude boosts. Because, well, the actual altitude of the ISS, if you look at a graph that plots it, it has actually been a matter of decrease, boost up, decrease, boost up, decrease, boost up repeatedly. And the overall operating altitude has been altered greatly many times over time. For example, when it rendezvous with the space shuttle, the ISS has to be relatively low because the space shuttle can only carry so much stuff up there, and if the space shuttle has to get up to a higher orbit, that costs more energy. So the ISS uses its own engines to boost itself and whatever the space shuttle happened to have delivered up to a higher orbit. Now, if you and whatever's around you are all falling at the same rate, such as in the free fall airplane flights where they train astronauts to deal with feeling of weightlessness, you end up with this quote applying. Now, this quote is incredibly commonly misquoted as from Buddha. It's not from Buddha. It's first found in Ernest Wood's 1971 Zen Dictionary on page 91 to 92. The first misattribution to Buddha was sometime less than 10 years after he released this book, which is kind of sad. So the foot feels the foot when it feels the ground. Why do you feel like you have weight? Well, you feel the ground pushing up on you to prevent you from accelerating through the ground because of the force of gravity. But if the ground is falling away beneath you at the same rate that you yourself are accelerating from gravity, you aren't going to feel anything. You feel weightless. Your feet barely count as touching the ground. In fact, just the sensation of touching the ground is enough to push you away from the ground. Because that requires that your feet sense force exerted on you by the ground in response to you exerting force on the ground with your feet. Okay. Gravity provides a uniform vertical acceleration, which means that we can use all the same old uniform acceleration equations as before, except we use g for gravity instead of a for acceleration, and we usually use h for height, although sometimes you do see d for distance, because after all, vertical distance, well, that's still distance. Okay. Or change in height is still change in displacement. Or change in position. Although positions are displacements from the reference point. and heights are from some reference height. Usually it's ground level, but sometimes you can be like, oh, this marble is 1 meter below the level of the desk. How much energy has to be given to it to raise it 1 meter above the level of the desk? Well, you're going from -1 meter to +1 meter with the desk as your reference. Okay, example 1. A skydiver on a plane drops a metal ball from 1,000 meters above the ground. If there is no air resistance, how long does it take the ball to reach the ground? We are using 9.8 for our gravity. What do we know here? We know V initial, gravity, and change in height. What do we want? We want how long it takes the ball to reach the ground. So we want the time. You could also write required delta t. Which equation is suited for this? Well, we know that delta h is going to be the area under the curve, and because this is going to be a trapezoid, because uniform acceleration for velocity time means a straight line, we know that V initial is 0. In this case, it's going to be a triangle, and that means equal to V initial delta t plus at is your change in velocity. So acceleration times time is change in velocity. So gravity times time is the change in velocity in this case. And delta t squared. Because you want that additional velocity to be multiplied by the time. Now delta h is from 1,000 meters above the ground to 0 meters above the ground, which means -1,000. And V initial is 0 times delta t plus 1/2 times -9.8, and delta t squared is still that. Now we can cancel out the negatives, so we end up with delta t squared times 4.9 is equal to 1,000. So, what does this come out to if we use fractions? Well, delta t squared is equal to 10,000 over 49. That says that delta t is equal to 100 over 7 seconds. Now there's a bit of a problem here. If you tell somebody that, oh, this process is going to take 100 over 7 seconds, that's a number that is a little bit awkward for them to use for hopefully obvious reasons, which means that we should approximate. How much should we approximate to? 1,000 meters above the ground. That's 4 significant digits. And we treat gravity as an exact value, so therefore 100 divided by 7 is approximately 14.29 seconds. It takes approx 14.29 seconds to hit the ground. The ground.